Hi everyone, welcome to the talk about NatGen, generative retraining by naturalizing source code. My name is Shoikat Chakraborty and I am currently a senior researcher at Microsoft Research USA. This work was done when I was a PhD student at Columbia University in collaboration with University of California at Davis. In recent few years, machine learning, specifically deep learning methods, have been used at a wide variety of applications in software engineering, ranging from coding, testing, bug finding, bug fixing, documentation, etc. If we look closely into a deep learning model, taking some input and producing some output, we can realize that there are two conceptual parts in any model. One part of the model is responsible for reasoning about the language, and another part is responsible for reasoning about the task at hand. Although, in all fairness, there is no explicit separation between these two components, nevertheless, we can see a conceptual division of these two submodules inside a model. Nevertheless, the language model of a component of a model is not dependent on any task, thus amenable to pre-training from a large corpus of data. Now, let us look how some of this pre-trained model works. One pre-trained language model, PLBART, is an encoder-decoder based model which takes in a code, injects some noises into the code, and generates a noisy code. Then the encoder and the decoder is asked to generate back the correct code from the noisy code. In the process, it learns how to generate the code. Since the model learns to remove noises, we can argue that the knowledge the model learns depend on the noise functions. And since PLBART use token level noises, we argue that PLBART learns token level semantics. But if we look closely into the source code, we see that there are two information channels present in the source code. First, there is the natural channel consisting of token level informations, including human readable variables and identifiers, etc. On the other hand, we see the semantic information present in the code, including the abstract syntax tree, the control flow graph, the data flow graph, different kind of dependencies, etc. Thus, in this work, we investigate whether we can inject noise in code semantic space and generate a noisy code in semantically noisy code from the code semantics. And then we will ask the model, encoder-decoder based model in particular, to take in the noisy code and generate back the correct code with semantic preserving formal channel mutations. In order to do so, we first take a piece of code. We then extract the abstract syntax tree out of it, and then we identify the possible locations in the AST to inject semantic noises. To inject noises, we design 6 classes of semantic preserving transformations, and we call these transformations denaturalizing transformations. After applying such a transformation, we adapt the context of the transformation code and finally generate a code that is semantic equivalent yet looking different from the original natural code, and we call this code unnatural code. Like I said before, we use 6 classes of denaturalizing transformations. Let us look some of those denaturalizing transformations. Suppose this is a correct code written by the developer and taken from a repository. The first transformation that we use is a loop transformation, where we replace the while loops present in a code with the semantic equivalent for loop. In the case of for loop, we do the other way. That is, if there was a for loop, we replace that with a semantically equivalent while loop. Another transformation we use is the insertion of a date code. We randomly use some block of code in the original code, making sure that that block of code will never execute. Another noise functions include swapping the blocks and swapping the operand of the conditional operator. And then we insert confusing code elements. And finally, the final transformation that we use is where we rename human readable variable names with symbolic names such as var1, var2, etc. Thus, using one of these transformations, we transform a correct code to a noisy code, semantically noisy code. And then we use an encoder-decoder based model in NatGen to transform the noisy code back to the correct code. In the process, since the encoder consumes the noisy code, the encoder learns to reason about what a input code is, and since the decoder learns to generate the correct code, the decoder learns how to write semantically correct code, more natural looking code in the process. Using these transformations, we generated a pre-training dataset consisting of more than 8 million code examples across 8 different languages. I do agree that this dataset is not nearly as large as whole GitHub, but with this project, we show a proof of concept that the naturalizing source code can be used for pre-training encoder-decoder based models such as NatGen. We evaluated the pre-trained model in NatGen in 3 different generative tasks, including code generations, where the input is the text and output is the code translations, where the input is a Java code and the output is the C# code or vice versa, and bug fix, where the input is a bug code and textual description of the code, and the output is the fixed code itself. Here is the evaluation results on NatGen in comparison with other state-of-the-art baselines, models, and techniques for different tasks. And as we can see from the results is that NatGen outperforms or performs comparably with respect to other state-of-the-art pre-trained models and techniques across all these different tasks. However, the most influence of NatGen is its ability to write correct code without any fine-tuning. To validate that hypothesis, we did an experiment where we asked NatGen and Codify to generate code for different tasks without any fine-tuning. We call this as a zero-shot evaluation. And as we can see that NatGen generates significantly higher number of syntactically and semantically correct code in contrast to the Codify across different tasks. We conjecture that since NatGen learns to write syntactically and semantically correct code as this pre-training objective, NatGen actually learns the ability to write correct code is inherent in NatGen. When we ease the problem a little bit and use 200 examples for fine-tuning, we see that Codify started learning about generating syntactically, semantically correct code, but NatGen is still retaining its knowledge that is it learned from the pre-training step. In fact, we see that with the increased size of the fine-tuning data, Codify and NatGen converges gradually. But when the fine-tuning data is very scarce, the difference between NatGen and Codify is most pronounced. Since we started pre-training NatGen from Codify checkpoint, we wanted to investigate whether NatGen is retaining the information learned in Codify. So we evaluated NatGen in code summarizations, and as we can see, NatGen performs comparably with Codify in code summarization as well. So the lessons we learned in this work is that semantic preserving rewriting can teach model write robust code, and teaching these rewriting tools to explicitly to the model can actually embed the PL-specific reasoning ability into the model. And as for extending this idea into the future, this idea can be used for learning semantic style transfer across different organizations or projects. And this idea can also has a potential to be used for automatically learning code refactoring. A huge shout out to the team for the hard work for making this project as a success, and thanks to the friends and colleagues for their valuable feedback in this work. Thanks for attending today's talk.